Let's all just keep breathing in and out, huh? And hopefully resting on the Lord. So quadratic functions and models. That's where we're going. But first, polynomials. My question to you is, looking at... Never mind. He's not going to move. Okay, so looking at this expression. Is this a specific polynomial or a general one? How do we know? There's n's. But wait, aren't there like 2's and 1's and 0's too? But are there coefficients? No. So that's kind of general, right? A is in lieu of or in the place of coefficients. Why do I have different A's? Any ideas? Yeah, there could be more than one number. It doesn't have to all be like 1's or 2's or 3's, right? I could have a 1 and a 2 and a 3, or a -2 and a 7 and a 10, whatever. So, first of all, the A's make it general, and then what else makes it general? Nathan was right. The N. Question. In relationship to all the other powers, what's true about N?
It's a number. Doesn't that mean
Yeah, but they're all numbers. It is a
It
constant.
doesn't equal 0.
It probably won't equal 0, but it could.
But
It's not negative. It's a variable. It's not negative.
Not negative.
It is not in fact a number.
It probably won't be negative. Actually, it definitely won't be negative, but none of them are negative. Oh. What's different, or what is special, or what's
It's an integer.
ends? Yeah, but they all are.
It's just a variable function.
It's a variable that stands for a constant, though, but so does that one. It's what?
A line and then a curve, and that makes sense.
It's a line.
If n is 0, it's a horizontal line. If n is 1, it's a diagonal line. If n is 2, it is a curve. It's a quadratic. If n is 3, it's a cubic. If n is 4, it's a quartic, which could look like that, or even like a W. But n can be lots of different things.
Power.
It is a power, but so are the rest. What is n's relationship to the rest?
It's the same thing.
How do we write polynomials? In what order?
Descending order.
Descending order. What does that mean? Why is it descending? The coefficients are descending. No.
The
The powers.
The powers of x are descending, right? So if the powers of x are descending, question, what does that make n, or the one that comes first? The highest power, right? So n is the highest power. That's a quick description of him. He's the highest power of x in a polynomial, which is why I said sometimes he could be 0, because a polynomial technically could just be y equals a number. Or he could be 1, y equals mx plus b. Or he could be 2, y equals ax squared plus bx plus c, etc., etc. N just denotes the highest power of x. Does anybody remember the really specific algebraic term for the highest power of x?
Nth power.
It is the nth power, that's true.
Leading.
But there's a really specific term if we're trying to look at a polynomial and describe his power, his magnitude, his greatness, kind of. We use this number, the highest power, and we call it the polynomial's what? Degree. I was going to start giving a hint about temperature. My catchphrase and try to make you guess it. Anyway, degree. The degree of a polynomial is the highest power of x. The degree of a polynomial is the highest power of x because, in essence, even though all these in-between terms, all the lower powers of x can definitely and do impact the overall polynomial, at the end of the day, meaning as we go to the right and to the left, the highest power of x takes over. The highest power of x has the greatest effect. All right, let's keep going. So this is in general. This is a polynomial. We're going to talk about all sorts of different polynomials as we move on. But to do that, we better start with the basic one. Wait, what's the basic one?
Polynomial.
What's the basic polynomial? A horizontal line, which is y equals c, or d, or a number, right? Have we already talked about horizontal lines though? Okay, the next highest one would be if x is 1. If the degree is 1, that would be y equals mx plus b. Have we talked about him? So then the next highest one would be too far, the quadratic. So here, like, well, we've talked about him, true, but we've also talked about cubics and absolute values and square roots, but we didn't talk about them in depth. We talked about the parent function, the easiest one. Then we said, hey, you can translate the easiest one. You can even stretch the easiest one or flip it. But we didn't go in much more detail than that. So this section is, let's get deep in quadratics. And let's hopefully figure out what our weaknesses are from the past stuff that we've done with quadratics and get stronger and get better. So first of all, degree. We just talked about degree. What's the degree of a quadratic? 2. Good. The highest exponent for a quadratic, the highest exponent would be n equals 2. Equation forms. To make this simple, let's just go here. Our book teaches it a little bit differently than I have in the past. Hopefully you guys aren't. Oh, that's weird. It moved over. I'm going to add in one more thing real quick. To make things a little bit more understandable with how our book describes them, let's actually throw in an extra piece called the definition. And it might sound a little funny when I put it down, but it's not a definition like other math terms. It's really just an equation. I'm sorry for those of you that are erasing. The real reason you use pencil because sometimes I mess up. So these. But the definition is the old-fashioned equation of a quadratic that we've talked about forever. I could go into lots more depth and say that a, b, and c have to be non-negative integers. No, they can be negative. Have to be integers. But that's the long story short. Y equals ax squared plus bx plus c. That's the definition. However, there is a much more useful form of the equation. But the problem is, it's a lot harder to get. Not a lot harder. It takes a little bit of work to get there. Ax squared plus bx plus c. It's great. It's great for a few things. This form is really good for, first of all, factoring. And we use factoring to find specifically zeros, and zeros are, taking a test. Right? So this form is really good for factoring and finding x-intercept. This form is also really good for, factoring fails. It's not nice factors, or they aren't nice factors. So then we go to something else called, I can't even talk, the quadratic formula. That form's good for the quadratic formula too. Why? Because quadratic formula has a's and b's and c's in it, right? X equals negative b plus 2 minus 4 b squared minus 4ac all over. Nice. Okay, so it's nice for that too, but it's not really nice for anything else. But there is a better form, and the better form is also useful for finding the transformations, seeing the transformations, seeing the vertical shift and the horizontal shift if there is one, and the stretch. And we talked about how for parabolas, a vertical stretch can be the same thing as a horizontal compression, so therefore we'll just put one multiplication and leave it at that. But this form is great for seeing the transformations. Which means it's great for, there's an R and an M in there somewhere, transformations, which means it's great for graphing. And another thing it's great for is finding, hey, doesn't this form kind of remind you of something? What formula from last section, or last chapter I should say? Circle. And what did the HK stand for in a circle? The center. But think of a parabola with a quadratic. What's the most important point of a parabola? The vertex. So this one also shows us the vertex. And the vertex being H. Okay. The vertex being H. Okay. X minus H, remember, so if there's a positive in there, it would be a negative number. If it's X plus 2, there would be a negative 2 for H. And this one on the outside just acts the way that we would expect. But here's the dilemma. Question, is every polynomial able to factor into what we would call a perfect square?
No.
Sadly, no. What if I was to give you something like, this is on the next page, do I have an example written? Nope. Okay. What if I was to give you something like y equals, go and just do an example. Let's do an easy one. X squared plus 5x plus 6. Okay. If I said to factor, what would you do? Think about 6. Think about the numbers that multiply to be 6. 1 and 6 or 2 and 3. And figure out which one adds to be 5, right? Maybe a few of you would actually go over and do this whole thing and then think about it this way. Either way, which one works? Adds to be 5. 2 and 3, right? We end up with x plus 2 and x plus 3. What is this super useful for? Finding zeros. That's great. We have the x-intercepts, negative 2 and negative 3. Yay. But what don't we know? The vertex. We don't know where the vertex is, and that's the most important point of the parabola. And we don't know how this thing has been shifted, right or left. Now, some of you might be like, well, I can think about it. And I can think. I know. If I have a 0 at negative 2 and negative 3, it's a really tiny parabola, and it somehow goes through this. So it's been shifted and then shifted. Okay, maybe. But can you tell me exactly how? Probably most of you know. So how do we go from here? There is a way, and we'll see it on a future page. It's actually the little cheater shortcut, but it's not always short. The other way to do it, which this is, once again, really great, I'm literally writing it, for zeros. Because I can find this function has negative 2, 0, and negative 3, 0 as points. But I'm going to say it's not good for the vertex. So here's the dilemma. Is this a perfect square? Not yet. Wait, not yet. Not yet. But it can be. What am I doing? I'm saying that 6 isn't working for me. It's not getting me a perfect square. If only I could have something else. And we can put something else. Algebra tells us we can add or subtract to one side of an equation. We just can't throw everything off balance. So if we have an equal equation, which we do from the very beginning, and if we add something to one side, what did algebra tell you? Add to one side and add to the?
No.
Oh, it's easy. We don't want to add to the other side. We want y to stay by itself. So if we add to one side, what's another way of staying balanced? Subtract somewhere else from the same side. If we add to one side and subtract it somewhere else, we're still balanced. So if we add something here and subtract that same something over here, it's still going to stay balanced as long as those numbers are the same. And some of you are like, well, what was that point for? Or what's the idea? We can group, you've done grouping before, we can group these. And let's see what happens. How could I make x squared plus 5x plus blank a perfect square? I wish 25. 25 factored, 5 and 5 can't make 5, I could only make 10. Struggle. Hold on, think of what I need. 2.5. 2.5 squared. Now some of you love decimals and that's all well and good. Maybe you can be an accountant someday, but for the rest of us, we need fractions. Just saying we need fractions. Because if I asked you, some of you guys, what 2.5 squared is, A, you would go to your calculator, and B, if you didn't have your calculator, you'd probably give up.
Yes.
Even though you've learned this since elementary school. Struggle. So what if I said you had to square it? Because to fill in one blank, we have to fill in the other blank. So if you don't want to do that, then what are we going to do? Write it as a fraction, and then say square 5 halves, and we'll say, psh, that's easy, that's 25/4 without having to worry about that. So if you like decimals, sweet, you better be willing to do this. Maybe we'll stick to fractions. If we have 25/4 here, we need to put 25/4 over here, true? To keep everything balanced. What did we just do? Take the square root. Remember, we thought it was 25, square rooting that 5 and 5. Didn't work. That wouldn't have come out. But now I can say x plus 5 halves squared. If you don't trust me, FOIL it. What's 5 halves times 5 halves? And what's 5 halves x doubled, because you're going to have an outer and an inner, the same exact term. 5 halves plus 5 halves is 10 halves, and 10 halves is? Bingo. Struggle. Now I have to do 6 and 25/4. That's not a big deal as long as you say, who is 6? In terms of fourths. Now you could do the old-fashioned way times 4 over 4, and that works. Or you could say, I have fourths, a pizza cut in fourths, and I have 6 of them. How many slices? A pizza cut in fourths. 6 of them. 24 slices. No? You haven't done a party planning. If you go to Costco and they cut them in fourths, I mean, you can cut them in 8ths or 16ths, but whatever. If they cut them in fourths and you buy 6 pizzas, how many slices will you have for guests? 4 times 6 is 24s. Kind of trying to show main logic instead of just memorizing. But couldn't you do that too?
Yes.
All right, fine. 24/4 minus 25/4. No party planners in here, huh? And what do we have? Right? What can I now pull out of this form? Yeah. It's great for graphing because now I know my vertex, and my vertex is, do it correctly, x minus h. What's my h? Negative, right? Good. Plus k. What's my k? So the factoring thing's great. I mean, that's helpful. But I need the vertex as well. And the reason why I say it's great for graphing is because with a line, how many points did you need to make a line from geometry? 2. How many points do you need on a graph to make a parabola? 3. And not just any 3, 3 particular ones. Or at least I should say 1 particular one and then 2 others. 1 particular one would be the vertex. Take it there. The vertex being negative 5 halves is 2.5, right? Then we go down a 4. Bingo. Then we have our negative 2, 0, our negative 3, 0. Booyah. Got it. And there's one more reason why finding a vertex is so stinking important. Not just because of, please stay alive, 10%, okay. Not just for graphing, but also because, how else can we describe this vertex of this parabola in context with the heights of all the rest of the points? It's the lowest, it's the relative min, and actually for this function it's the absolute minimum. And why on earth could a minimum be an important thing? If you have to, not if you have to, but if you have a business, you have two main components to that business. Cost and profit, right? What do you want to do with your cost? Minimize it. As you, what do you want to do with your profit? Maximize it. Minimax, that's a pretty huge idea in context of things like economics. All right, let's keep going. Ah, stink-a-dink. What's this whole page for? Did you just watch me complete the square? Why, yes, indeed you did. Does that mean everyone is a master at it? No, probably not. So let's go ahead and just take a little bit of time. Let's write down and remind ourselves of the steps so that we can refer, you can refer specifically back to it in homework. And then let's do a few more examples because believe me, I know and I understand that this is a hard one to master. Take a few seconds. This is my quick shortcut for how to complete the square. The book probably has like a much longer, more complicated, more in-depth description. And I'm sure the dozens at least of math tutors online all have their own way. But this is my way, at least it gives you one way. And if you need more ways, this is the technology age. Go find some. To get from the definition to the standard form, which I like to call the vertex form because it has a vertex. Clearly there so you can hold it. The very first step, get a leading coefficient of 1. And leading doesn't just mean the first one written. It means the coefficient by the x squared term for a quadratic. You guys are setting it up, but let me go ahead and start filling it out. That way we actually have something. So, leading coefficient of 1. In the general one up above, what was next to x squared? A. And if A is anything other than 1, the last example was a 1. It was easy. It already was a 1. We were good. But what if it's anything else? Look at the standard form. What happens with that A? It gets factored out. So, leading coefficient of 1, factor out. Factor out any non-1 A's. That's a weird way of putting it, but basically it's like, hey, as long as A isn't 1, we have to factor it out. Factor out the leading coefficient if it's anything other than 1 from, now here's an important part, the x squared and x terms. What did I not say for that definition? Don't take it away from the constant. Long story short, the constant's not good enough. We saw that in the one before. The constant 6 was great for factoring in x plus 2 and x plus 3, but that's not a perfect square. I have to move that 6 off to the side. Still keep him, because he's a part of my equation. But I'm looking for something better. Factor out the non-1, or any non-1 leading coefficients from the x squared and x terms only. Form a perfect square. How? By adding in. How did we find that 25/4 in the last example? Do you remember? Divide what by 2? The middle term coefficient. So dividing the x coefficient by 2 and then squaring it. Taking the middle coefficient, or a better way of saying it is the x term coefficient after factoring out the a. Take the coefficient of the x term remaining, cut it in half, and then square it. Cut it in half and then square it. And a quick hint, if we're trying to get to x minus h squared, after we put this special part in, and when we go to factor and simplify, actually, you know what? I know. You can have groans for, oh, she's changing something. You know what? That belongs in that step a little bit more. Oh my goodness, I know it's right. It's okay, just erase the H and make your brace a little bit taller. How do we keep the equation balanced? We could add to both sides, that's one strategy. We could add or subtract to both sides. That's the old-fashioned strategy that had to do with algebra. Some of you might not have left 2 lines anyway, so there we go. Add to both sides, that's the algebra one way. But then we saw in the one example before, in the page before, is that we could add and subtract from the same side. Add and subtract from the same side. Now, David, finish, just staple it and put it upside down my desk. Thank you, sir. Yeah. And then, last but not least, once we add and subtract the proper number, half the coefficient squared, then we can go ahead and factor and simplify into our nice standard form that shows the vertex. But if you have a little bit of trouble seeing what to put in that H spot, here's the hint. H is always going to be the x coefficient cut in half before you squared it. So some of you are just going to be able to see that and be like, oh, hey, I made my perfect square, and this is what it should be, x minus this number, x plus this number squared. But some of you it's going to be hard to see. So if you realize that you can really just steal to put in that spot whatever was here before you squared it, maybe that'll make it easier. And technically, there is a way to check with the definition, with the B's and A's from the very beginning. You can check and make sure you did it appropriately or correctly by using a little baby cheater formula, negative B over 2A, from the original form before we did any of this completing the square stuff. And if those two match, you did it correctly, and you have your H, and hopefully, as a result, you also have your K. Hopefully, as a result, you also have your K. All right, do we have all our steps done? Sort of, kind of, maybe? Let's go ahead and, hopefully, practice. Practice. Because of the book, I don't want to steer you guys wrong. I always call it vertex forms. If I accidentally say that, you know what I mean, hopefully, because it's the form where you can see the vertex. The book, though, calls it standard form. Go ahead and try to perform the steps that you have in your notes. Nice thing is, the leading coefficient is just 1 to the following. Ready, set, go. You are definitely allowed to collaborate in your groups. If you know what you're doing, go through and try it. This is someone in your group that's a little stuck. Maybe talk it out. It'll help you and them. Forever, but try to get all the way through to find the vertex. If you want to factor, you can. That's great for zeros, but that's not good enough. We need to get standard form. start. I'm not saying much. I'm just going to start working it out, and you guys can compare to your work and see if it matches. What was indicated?
Is it 12.25?
Point. Aw, you guys are using decimals?
It's a very. But 62 more.
No, I went. I really agree. It is 12.25. I went.
Look at how easy these fractions are. It's just saying.
Personally against my religion.
Sweet.
Dun, 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 dun.
Oh my gosh.
What happened?
I got it. I squared by 2 instead of squaring. So I did 14 on the.
Square it. 7 times 7. Do you guys see how I just stole the negative 7 halves for my x minus h?
Yes.
That's a trick. You don't have to worry about, oh, what would that be? You set it up so that you can literally just say, hey, that's square rooted. That cut in half is that h term. Do you see how easy, maybe, using fractions was? 48 minus 49, sweet, it's negative 1. How did I get 48? If you don't want to think about the pizza analogy, you can think about, okay, times 4 over 4. There you go.
Can't we just use a calculator?
I like this.
But here's the dealio. If I let you use your calculators, what would some cheaters do? Graph it and find them in. No.
That's what I'm talking about. I ain't even gonna be able to graph it.
I honestly
Do you
wouldn't
know there are
have thought
some college courses, if you make their math entrance, actually most college courses, you take a math entrance exam, you have to prove to them you really know the math that you took in high school, and if you can't prove it on the exam, they send you back, way back, to high school math. And then you have college professors that are purists, and they're like, calculator? No. Ever. I'm nice. I let you use a calculator from time to time.
What about next year?
But I'm preparing you. Calculus, there's a calculator part and a non-calculator part. So we have to know both. Calculator, great technology. However, have you ever heard the age-old, what if you're a cashier and then the electricity goes out? Wah, wah. Then you're like, I'll get my phone out.
That's why I have a battery
Okay.
operated calculator.
Woo! What do we do with this one? You're just going to carry it around like a little sheath in your belt? Like, haha! That's cool. All right.
I would totally do that. That's too easy.
Back before my day, where we became these things called slide rules. This was their calculator. Cool, like college math professors or math students before calculators had this all folded up and had it like in a pocket protector.
Nerd style.
That was before my time. What are you doing? Can I do it with you? It's a hard one. There's a number in front. You guys always take the numbers in front.
Factor it out.
Factor it out. I'm not doing the whole thing, but I'm starting because some of you might have gotten stuck at the get-go. What am I not pulling the 3 out of? We're used to grouping.
The 7.
Not pulling it out of the 7. You're just getting the form. Now, could you factor to get zeros? Yes. That's just not specifically what this one is asking.
But I don't know why I did.
It's because your brain is so used to seeing a quadratic and saying factor, which is sometimes good, but not always best. Okay, keep going. I have it now in the form which hopefully you can pick up with the other steps that we were doing. Take a middle number, cut it in half, square it, add it to both.
Wait, how are you allowed to do that? Like, not take it out of the 7.
Because the 7 wasn't good enough. He doesn't make a perfect square.
Just take 3 out of the
Who's done what? Take the 6 and cut them in half. What do you do once you cut them in? Alright, focus back on in. Take the middle term, cut him in half, and then square him. If that's a little too rough, 6 over 2 is?
Are you supposed to divide them in half?
That's what 6
Yeah,
over 2
wait.
is.
6
6 over 2
is 3.
Oh, yeah, huh. It's early.
Woo! What? Mind blown. What did I just do? It's the only proper way to go, though.
Tripled it.
Why'd I triple it? What's outside the parentheses? The 9 is really a 27. Is that the only way to make it balance? Once I put a 9, who is he really? See it? He's a 27, so if I add 27, what do I have to do out here?
So you can get rid of the 3. No, you can't.
Do we see the 27? There's a 3 outside. That 9 is really a 27, so to keep everything balanced, I'd have to put a minus 27. Now I need to factor, right? We know exactly the form we want to factor into. But question, who's the H? We can go up here and work through factoring in our heads, or we can say, steal the 3, right? Remember? The H is always just the number before it gets squared. Is it a positive or a negative? Well, look at the 3. Does it look like a positive or a negative? Yes, positive. There's no negative sign in there. If you want to check me, x plus 3 times x plus 3 is x squared plus 6x plus 9. That's right. And what's 7 minus 27? Plus a negative or minus
17. Oh, yeah.
See it? Don't worry. The higher you go, the harder the easy stuff becomes. And the vertex is x minus h plus k. Whew. It's a little far down. Now, just because we are working with quadratics, hold on, let me see what's over here. That's another idea. We'll do that tomorrow. We have 2 days on this. But wait. I'm a little worried about something. My little worried about something has to do with the whole zeros thing that doesn't even have to do with completing the square, and it just says, could you factor this quadratic? And what is my fear? That some people can't, and that's okay, because I understand why. There's a number in front. But can we just use the last couple minutes of class to talk about something you've been doing since Algebra 1 that still kind of throws you for a loop? How do we start the process of factoring? At least the way that you've been taught, as far as I know.
The y equal to 0.
Define the zeros, yes, set the y equal to 0, but how do we keep going?
Multiply the 3 and 7.
A times C, or first times last, and ask yourself the question, what factors do I have? Oh. Can I factor this one?
No.
No. What am I looking for? Just put it on my desk, Kelly. Thank you. What am I looking for? Can these make?
18.
Oh. Are there any nice factors?
No.
So how would we find the zeros?
Complete the square.
X equals negative b plus. Or,
Put it in your calculator.
don't I stop? Stop. You're deadening your mind. Can't I substitute? And say, oh, add the 20. Divide by the 3. Plus or minus square root. Wait. Subtract the 3. Guess what the quadratic formula would end in? And I didn't have to remember a song or anything. Kiddos, start your homework tonight. I'll see you tomorrow and we'll keep working on our quadratics. Everyone taking a test? It's on my desk, right?
Yeah.
Sweet. Oh, Haley, don't take it. You have to take it after school. I haven't graded it yet. People who still go through the back, make sure I still have them, or else your grade will be a 0. Try to get in.